In this video, we are going to talk about vector spaces and subspaces. We'll spend a couple of minutes going over this overview slide, and then we'll take each topic with lots of examples. So first we start with the definition of a vector space, which is a set of objects and then two operations defined on those objects. The first operation is addition, and the second is scalar multiplication. And to be a vector space, these two operations on our set of objects has to satisfy these properties. There are 10 properties. Two about closure, so that addition is closed and scalar multiplication is closed. And then a set of properties about addition, in particular that addition of two vectors is commutative, it's associative, there's an additive identity, the zero vector, such that v plus 0 equals v, and an additive inverse. So for any given vector in the set, you can find a vector negative v such that v plus whatever that addition, however it's defined, plus the inverse is equal to 0. And then you have properties about the scalar multiplication. In particular, there's some associativity with the scalars. There's this distributive property with the scalar and another distributive property involving scalars. And then the multiplicative identity is in the set. That is, this one vector, 1 times any vector is equal to the vector. It just returns back to the vector. And we'll do plenty of examples of vector spaces to get a good feel for different types of vector spaces. Second, we'll talk about subspaces. And a subspace is a subset of the vector v along with the two operations that in itself is also a vector space. And to prove that a subset is a vector space, you only have to prove 3 items, which is the zero vector and the two closure properties, because these other properties are simply inherited, so to speak, from your set V. And last, we'll talk about a special subspace, which is a subspace spanned by a set. So that concludes the overview. We're going to go and look at a vector space, definition of a vector space. So a vector space is a non-empty set V of objects that we call vectors. And then second, it has two operations. The first operation is what we call addition, and the second is called scalar multiplication. And the thing about these two operations is when you perform these two operations on your objects, on your vectors, they have to meet these properties. The first one is the first two are closure properties. That is, addition needs to be closed, as well as scalar multiplication needs to be closed. And we'll talk about closure in just a moment. That's the first property we'll look at. And then there are these properties of addition. Addition needs to be commutative, associative, there needs to be an additive identity and an additive inverse. And then we have our properties of scalar multiplication. There needs to be associativity, there needs to be a distributive law of this scalar, and then a distributive law when you have addition of two scalars, and then also you have to have a multiplicative identity in your set V. To look at these different properties, we're going to use Rn, where n is greater than or equal to 1, and Rn is sort of our canonical or premier example of a vector space. It's the one that everyone learns first and you're quite familiar with. And for this first example, just to kind of simplify things a little more, we're going to focus on R3, and we're going to show that R3 is a vector space. So looking at vectors in R3, what they look like is U is our first vector, and it's 3 tuples. So the vector u1, u2, u3, where u1, u2, and u3 are real numbers. Our vector v is v1, v2, v3. A vector w is w1, w2, w3. And then we also want to introduce scalars a and b. They are real numbers. And the first thing we want to talk about are closure properties. But before we go into closure using the vectors with vector addition and vector scalar multiplication, I just want to talk about closure in terms of other sets, just to kind of give you a better feel for closure. So if we consider the set of integers, so in particular, let's say we have x and y, and they are both integers, set of z, then the integers are closed under addition because when you add two integers, you get back an integer. So x plus y is still in the integers. Integers are also closed under multiplication because when you multiply two integers, such as x, y, you get back an integer. So you're still in the set of integers. However, integers are not closed under division because 1 is an integer and 2 is an integer, but when you divide 1 by 2, you're no longer in the integers. So this is a set that integers is a set that is not closed under the division operation. And let's look at another set. The set of real numbers is closed under addition because when you add two real numbers, you get back a real number. It's closed under multiplication because when you multiply two real numbers, you get back a real number. And it's closed under division because here, if you divide two real numbers, you get back a real number. So whether or not something is closed, it depends both on the set you're considering as well as the operation. Now we can go back to our set R3 and look at closure. So if I have two vectors in R3, when I add them, I get back a vector in R3 because of the component by component. So in other words, there's no way if I'm in R3, I'm going to get back a vector in R4. So for this reason, vector addition is closed it's closed. Second, scalar multiplication. When you multiply a vector times a scalar, because you're multiplying the scalar times each component, you're going to get back a vector in R3. So in this case, scalar multiplication is also closed. So therefore, R3 is closed under addition and scalar multiplication. So we've proven these two closure properties. I've cleared out the closure properties and the other scalar multiplication properties, just so now we could focus on properties of addition and have a little more room. So I have my properties of addition, the fact that we're working on R3, I have my three representative vectors u, v, and w, and my two real numbers. And I'm going to start with these first two properties. Addition is commutative, as well as addition is associative. To show that addition is commutative, we need to show that a vector u plus a vector v is equal to the vector v plus the vector u. So I start off with my vector u and my vector v, and I wrote it out as, R3 with the components. I add them together, and from here to here, all I'm doing is using the definition of vector addition. I'm adding component by component. Now, u and v are real numbers, and by real numbers, addition of real numbers is commutative. So I wrote that here, and I can swap the order of u and v. So now I'm going to have v1 plus u1, v2 plus u2, and v2 plus u3. But by vector addition, definition of vector addition, this is just vector 1, or vector v, plus vector u. And so in this way, I have shown that the vector u plus v is equal to the vector v plus u. We have shown that addition of two vectors is commutative, so now we need to show that vector addition is associative. So we need to show u plus v plus w is equal to u plus v plus w. So here I have u plus v plus w, and at the end I want to show that's u plus v plus w. So I've just rewritten this here in terms of my vectors, my R3 vectors, with written out as components u1, u2, u3, etc. So I have my u, and this says I need to add v plus w first. So I go ahead and add them, and I get v1 plus w1, v2 plus w2, and v3 plus w3 as one vector. Now I have, this is my new vector, and I can add the two vector. So according to the definition of vector addition, I'm just going to add the u1 component to v1 plus w1, u2 to v2 plus w2, u3 to v3 plus w3. But now you will notice this u1, v1, w1, u2, v2, w2, u3, v3, w3, these are all now real numbers. And real numbers, the addition of real numbers is associative. So I can associate u1 and v1 and add those together first. And I can add u2, v2 together first and u3, v3 together first. And again, I can do this now because these are real numbers. An addition of real numbers is associative. And once I have that, using the definition of vector addition, that's the addition of this vector, u1 plus v1, u2 plus v2, u3 plus v3, plus the vector w. So now here I can separate out my u1 from my v1, or my u from my v, and I get the associative u1 plus, or u plus v are added together first, and then w. And therefore I have shown that addition, vector addition, is associative. And you will notice in both of these cases, when we prove commutativity and associativity, we have our vectors and we break the vectors down into components, and then we do whatever we need, the definition of vector addition, so that then we have some real numbers. And then we rely on the commutative property, but now the commutative property of real numbers. Same thing here. We wanted to show association. We broke down the vectors so that we have the components, and the components are real numbers, so then we can use the associative property of the real numbers. So we wanted to prove associativity of the vectors, we needed to get down till we could use associativity of real numbers. Similarly here, when we wanted to show vector addition is commutative, we broke it down till we could get to the commutativity of real numbers. So now we have shown the commutative and associative property. The additive identity and additive inverse are pretty quick. So the first thing, to show the additive identity, you just need to demonstrate there's a zero vector such that v plus 0 equals v. So in R3, this is what the zero vector looks like. So when we take an arbitrary vector v and add it to 0, 0, 0, we get back our vector v. Similarly, for additive inverse, I'm going to check this one off. We just need to show the existence. We need to just basically demonstrate it. So if we're given a vector v, we need to show a vector negative v also in the space, in the set v, capital V, such that v plus negative v is equal to 0. So given a vector v that looks like v1, v2, v3, then there exists a negative v, and that's negative 1 times v. So negative v1, negative v2, negative v3. This is also a vector in R3. And when we add it to v, we get the 0 vector here, the additive identity. And now we can check off this property as well. So it's interesting because these two were showing some properties. These two were showing the existence, that there exists an additive identity, there exists an additive inverse, so we just need to demonstrate that we can find it. Here, the demonstration isn't saying there exists a 0, but like showing what the 0 looks like. Same thing here, the additive inverse, we show what the additive inverse looks like. So far we've done our closure properties, we've done our properties of addition. We need to now go to properties of scalar multiplication. Again, I cleared out our closure and our addition properties, and I left the properties of scalar multiplication just to give us more space. And again, we're looking at R3. We have our three kind of representative vectors, u, v, and w, and we have our two scalars, a and b. So for whatever reason, I decided I was going to show associative and the multiplicative identity on this slide. So we'll start with associative, which is a scalar a times this vector, and this vector is b times the vector v, is equal to the scalars ab multiplied together, then multiplied by the vector. So I start with a times the scalar b times the vector v, and at the end I should have that's equal to ab times the vector v. So I have a, and then I go ahead and multiply my scalar component by component, and I get bv1, bv2, bv3, and that's just by the definition of scalar multiplication, this x's multiplication. Now this is my new vector, and I can multiply a times my new vector, which means I just multiply each component by a. So I'm going to get a bv1, a bv2, a bv3, and again, this is also just by definition of scalar multiplication. And now, AB is a new scalar, so I can factor it out. And again, this is by definition of scalar multiplication. It's funny, all of this is just definition. And now I have A times B times the vector V. So I can check off now associativity. My next thing I'm going to show is multiplicative identity. And notice this is a scalar. So there's a scalar called 1 that when you multiply by V, you get back the vector V. So multiplying 1 times V gives you back the vector v. So this is my multiplicative identity, and it's a scalar here. So next, that's why I did this one, because I wanted to do the two distributive kind of properties together, and it's distribution of scalars. So the first one is a times vectors u plus v should equal to a times u plus a times v. So that's the one we'll do first. Looking at a times u plus v, so I substituted this R3 version of u, R3 version of v, and then I added them together just using definition of vector addition. So it looks like a times u1 plus v1, u plus v2, and u3 plus v3. Now, by definition of scalar multiplication, I can multiply a times the first coordinate, and then a times the second coordinate, a times the third coordinate. So here I've multiplied a times u1 plus v1, a times u2 plus v2, a times u3 plus v3. And now I can do this just distributive law because now we're looking at real numbers. A is a real number, u1, v1 are real numbers, u2, v2 are real numbers, and u3, v3 are real numbers. And multiplication of real numbers is distributive. So I'm going to distribute my a in, multiply a times u1, and then I have plus a times v1, a times u2 plus a times v2, and a u3 plus a v3. And again, this is another example when we're looking at this distributive property. We break down the vector until we have real numbers over here, and then we can use the property of real numbers, the distributive property of real numbers. And now, by using the definition of vector addition, we can separate out this vector from this vector here. So we have AU1, AU2, AU3, plus AV1, AV2, AV3. And now using the definition of scalar multiplication, we can pull out the scalars. So now we have AU plus AV. So we have shown that A times U plus V is equal to AU plus AV. This distributive property here is now done. Moving on to this distributive property where we have the addition of two scalars times a vector is equal to the scalar times the vector plus the second scalar times the vector. So we will prove that over here on the right. We have two scalars, a plus b times a vector v. So I write out my vector v in terms of its three coordinates. So now I have a plus b times v. By the definition of scalar multiplication, I'm just going to multiply my scalar a plus b times each of the coordinates. So I have a plus b times v1, a plus b times v2, a plus b times v3. So now you might recognize this. The a and the b, they're real numbers. My v1, v2, v3 are real numbers. So now we can use properties of real numbers. In particular, now we can distribute. We can have this AV1 plus BV1 multiplying V2 by each of them, AV2 plus BV3, and here's a real number multiplying each of A and B by this third real number, V3, AV3 plus VB3. Again, now we're using the distributive property of real numbers. That's the fourth example of when we wanted to prove a law about vectors. We break the vectors down until we have real numbers and use that same property now of the real numbers. And finally, now we can break these two into two vectors using the definition of vector addition, and we get AV1, AV2, AV3, plus BV1, BV2, BV3. And finally, we can pull out the scalars by the definition of scalar multiplication. We have A times V plus B times V. And we have proven this last distributive property now. So now we have proven these 10 properties for R3 with the vectors in R3 with the addition defined as regular vector addition and scalar multiplication defined as regular scalar vector multiplication. So we've proven that R3 is a vector space. Your book did a very short kind of description of why Rn was a vector space, but I thought it was worth going through each of these steps in detail just so you could see it at least once. So there'll be some things that'll be sort of hand wavy like your book, and other things I'll do a couple of more examples that's in more detail, just again so you get the idea if you needed to prove it in detail. So this next example will be a little bit hand-wavy, but the reason why I wanted to introduce this example, because it will show you how powerful or how widespread vectors are. So let's think of waves as vectors. And we define addition as the superposition of waves much like you learned in physics. So if you wanted to know how to add two waves, here we have wave 1, which is in blue. We have wave 2, which is in green. And then we have the sum of these two waveforms, the blue and the green, which is in red. And the way we're going to define now vector addition is superposition of waves, which you might have learned in physics. You basically go point by point and add the value of wave 1 to value of wave 2. So at this point, at this black line, both the blue and the green wave are at 0. So our sum of two waves, the red wave, is also going to be at 0. And forgive me, I moved my little grid lines around a little bit so that I could line things up. So if you look at this black line over here at this time, our blue is somewhere right about 0.5 and our green is a little bit above 0.5. So you're guessing that the sum should be something a little over 1, which is exactly where the red is, something a little over 1. So again, just you pick a point along the axis. That usually we think of the axis as being time. So some point in time, then you figure out the value of wave 1, the value of wave 2, and to get the red wave, you just sum the 2 points together. So it's kind of point by point, called superposition of waves. Scalar multiplication, so if we have this black line, point by point, if we're going to multiply it, say, by the scalar 2, you just take each point of the black line and you multiply it by 2. And essentially you stretch out your waveform by a factor of 2. So that's how we define vector addition and scalar multiplication. So now looking at these properties with both our vectors, those are the waves, and our two operations, addition and scalar multiplication now defined, we can kind of talk about these properties to show that they are a vector space. So first, the closure properties. So when you add two waves, you're going to get a wave, and you can kind of see that intuitively. Also, when you scale a wave, you're still going to get back a wave. So you can see that's kind of intuitively true. Commutative, right? It doesn't matter if we add the green or the blue, because at some point we're just adding point by point, going back to the real numbers, the addition's commutative. So it doesn't matter if you do u plus v or v plus w. It doesn't matter if we do green plus blue or blue plus green. Associativity is sort of the same. Additive identity, so let's identify the 0 vector of our waves. And that's a wave where, given any other wave, you get back your original wave. So the 0 vector, I'm drawing it in black here, is the vector along the x-axis. This is our 0 vector, because any vector added to the 0 is going to give you back your starting vector. For the additive inverse now, so if you have a waveform, you want to find some other waveform that when you add to it, you get the 0 vector, or the flat line. So let's just pretend like our vector is this blue one, the two times the black. To get the inverse, what I need to do to this blue curve is just flip it over the x-axis. So now when I add them together, I will have the 0 vector. So that's the additive inverse. And then you can kind of think about the associative properties, but this is mostly what I wanted to tell you, that to kind of give you a demonstration that these waves are in fact a vector space, and give you a kind of a feel for how you would prove that. And the reason why I think this is such an important example is the number of places we can find waves, or the number of places we can represent things with waves. And what comes to mind immediately is light and sound. So all of these things are vector spaces. And once you identify it as a vector space, everything we say in this book applies to these type of problems. And so one of the important things to do is, when you understand what a vector space is then go and find where you can apply this knowledge and find new vector spaces. When I was at Riess, I remember one of my vector calc teacher had discovered a new vector space, and it was a big deal. So one of my favorite projects I used to give when I taught linear algebra to students was I would ask them to go and find a vector space, come back to the class, tell me what it is they thought was a vector space and why. And if they thought something was interesting, but it wasn't a vector space, they would need to tell me, well, these are the things these are the conditions that it satisfied, and these are the conditions it didn't satisfy. And maybe, kind of play with it. If you could alter it some, what would it look like? So one of my favorite examples, and there were a lot of good examples, but one of my favorite was the game Rochambeau, otherwise known as rock, paper, scissors. So Rochambeau, that's rock, paper, scissors, and the idea is it's played between two people, and you have your fist and you say Rochambeau, and on the third count, on when you say bow, then you make either a fist to represent rock, a flat hand to represent paper, or the scissors looking fingers to represent scissors. And then you would play this game and someone would win. And the vector addition, so the vectors now were the three different plays. The vectors were rock, paper, scissors. Then the operations would be who would win. So if one person had rock and someone else had paper, then the winner would be, the paper would wrap around the rock. So the winner would be paper, sorry. If you had rock, someone had rock and someone else had scissors, the rock could pound the scissors, so the winner would be rock. If someone had paper and the other person had scissors, then the scissors would cut the paper, so the winner would be scissors. And if two people had rock, it would be a tie. So I guess the winner would be rock, and paper would be paper, and scissors would be scissors. But that would be the addition property. The scalar multiplication, so usually you don't have scalar multiplication in this game. And so what they said is, maybe you had to commit. So maybe you would write on a paper 3 different plays you would make, and then you had to make those 3 plays, and then you would just, so if you say 3 rock, that means the next 3 times you played, you would have to play rock. Of course, it wasn't that interesting a game that way, but that's kind of what they would define scalar multiplication as. Closure, is it closed? Well, it is, because, when you do your addition, you always come back with rock and scissors. Scalar multiplication, you still come back with some flavor rock, paper, scissors. And then the big problem also, another big problem other than scalar multiplication, is what is the additive identity? Because you don't have anything that always loses. So in other words, if you say rock, the winner's always rock. So I think they came up with a 4th hand symbol, and they said, maybe if you're playing with a child or something, or you're playing a long game and somehow, I don't know, you want to act dumb, I don't know. But there was this one other symbol they came up with, which always lost. And so that was like the additive identity. So Rochambeau was an example of something that did not quite fit a vector space, but it was interesting because you could define vectors, you could define an operation, you could, and it met some properties, but others we had to kind of fudge or make in there. It was a very interesting presentation. And again, the point of this, though, was to be able to expand your idea of what a vector and a vector space is. It's not just Rn. There are many things that are vectors. So another example from your book is the set of all arrows, or directed line segments in 3-dimensional space, with 2 arrows regarded as equal if they have the same length and point in the same direction. Then we would define addition by the parallelogram rule, like we had when we added vectors for each vector in V, and define CV to be the arrow whose length is C times the length of the vector pointing in the same direction, if C was greater than or equal to 0, and if C was less than 0, then pointing in the opposite direction. And we want to show that V is a vector space. So this space is a common model for physical problems of various forces. We are going to hand wave a lot of this, but we'll start with looking at closure. And almost by definition, addition is closed. So if we had, for example, this vector plus this vector here, and actually the vectors are the arrows. So we have this arrow here and this arrow here. If we want to add them, we're going to use the parallelogram law. And from the other chapter, remember, you can move vectors around. The only thing that defines your vectors are your length and direction. So if I move this, ideally I didn't change their direction, and the length is preserved, so I can do the parallelogram law to produce this new arrow here, So by definition, it's still a vector, or an arrow, a directed line segment. Scalar multiplication, again, if I multiply by something and it scales it, let's just say twice as long, right? It's still a directed arrow. So it's closed according to these two definitions. The rest of this, we're going to hand wave, things like commutative law. If you add u plus v, it shouldn't matter if you do v plus u. Sort of looking at three vectors, if I have a third vector, v plus w, let's say this is v and this is w. Here's my parallelogram law for v plus w. And I know that this problem defined addition in terms of the parallelogram rule, but probably the easier way to see this is when we do this associative property, is if we do this form of adding vectors where we add them end to end, which, as we learned when we did vector addition, is equivalent to the parallelogram law. So now if we add a third vector u, here's our vector u, we can move it then end to end. So our resulting vector goes from the origin to here, because we've followed the three vectors. So here in green, I have my u plus v plus w, and I also just labeled u here, w here, and v, so that we can see if we now do u plus v plus w. So now I can move v over here, so I add it to u, and then I can add w to the head, and you can see the vector I get ends over here at the same point, and so I get the same green vector. And you can kind of think of it, since we're going, vector at tail of one end to the head of the other, it's just like if you walk, 2 blocks north and then at a 45-degree angle, which is what that would be southwest, 2 blocks, and then like a little over 3 blocks, going northeast. You're going to get to the same place as if you walk northeast first and then southwest and then north. So this is the associative law. So this was extremely hand-wavy. We certainly didn't show this for all vectors. I just kind of drew some pictures for 3 vectors, or 3 arrows. But the fact that this is associative shouldn't surprise you, because honestly these arrows, we know that they can be represented as vectors in R3. In other words, we can represent them as the arrows, because this is what we do all the time with vectors. We can represent them as something in R3, and we've already shown that R3 is a vector space, so it definitely follows the associative law. Just to do a couple other things, the additive identity is just the single point at 0. And the additive inverse is, the arrow pointing same length, pointing in the opposite direction. So this would be, if this is v, this is the inverse of v. And when you add them together, you're going to get the single point 0. And then the properties of scalar multiplication, again, you can kind of see how that would work out. And to excuse my hand waving again, I'm going to appeal to the fact that these arrows can be represented as the vectors that we've been working with in R3. Another example as a vector space, let S be the space of all doubly infinite sequences of numbers. And by doubly infinite, that means we go to negative infinity on one side, positive infinity on the other. So usually written in a row rather than a column. And you can imagine if it were written in a column, it looks like vectors in Rn, except that here n is like infinite. So if y sub k, that's one sequence of doubly infinite sequence, and then we also have another z sub k, another infinite, doubly infinite sequence, then we're going to define the sum, y sub k plus z sub k, as a sequence formed by adding the corresponding terms of y sub k and z sub k, much like we do when we add vectors in R3 or Rn. The scalar multiple c sub y sub k is a sequence c times y sub k, and the vector space axioms can be verified much the same way as Rn. Again, it's actually exactly the same, except now you have infinity on both sides. So elements of S arise in engineering. For example, when a signal is measured or sampled, discrete times. Digital signal processors use discrete or digital signals. So for the convenience, we will call S the space of discrete time signals. And a signal may be visualized by a graph, as in the figure below. So you can think you have this waveform, maybe it's an audio waveform, but when we measure it, we can only measure in discrete samples. But this discrete samples is like 0, 0, 0, 0, 0, 0, or maybe this went up a little bit, but let's just say it's 0. This one looks like 2. This is like 2 point something. Here we have 3, and then it's coming down. You can take all these zeros, the 2s, the 3s, and you can keep going on, and that will be your discrete time signal. That is something like this S, the doubly infinite sequence of numbers. This next example is important and interesting. For n greater than or equal to 0, the set of P of n, of polynomials of degree at most n, that's that subscript here, consists of all polynomials of the form pt, this is a polynomial with the variable t, is equal to a naught, that's a scalar, plus a1t plus a2t squared, all the way up to a n t to the n. And here, as I mentioned, the a naught, a1 up to an, and the variables t are real numbers. The degree of p is the highest power of t whose coefficient is not 0. And if all the coefficients are 0, p is called the zero polynomial. The zero polynomial is included in Pn. So we can show that Pn is a vector space. The properties I will start with is the closure properties. So I'm going to take P is one polynomial of degree n and R as my second polynomial of degree n. Now when I add my vector P of t with R of t, I substitute my expansion of P of t, and I substitute my expansion for R of t. But now, because I'm dealing with polynomials, you know I can group my coefficients of 1 together. I can group my coefficients of t together. I can group my coefficients of t squared together up to t to the n. I can group those coefficients together, but now these are just two real numbers. So I could write this as c naught, my new real number, but essentially I have the same form of p of n, which is a scalar plus a scalar times t plus a scalar times t squared, all the way up to a scalar times 2 to the n. And you can see if we're adding two polynomials whose highest degree is n, there's no way you're going to get to p of n plus 1, right? If you're adding a second degree polynomial to another second degree polynomial, no way like a t to the fourth is going to appear out of nowhere. So this is how we know that it's closed under multiplication. Showing closure under scalar multiplication is similar if I have a scalar a, so a is a real number, times my polynomial p, plugging in the form of polynomial p. I can see that when I multiply everything out, I'm going to have a scalar plus a scalar times t plus a different scalar times t squared, this should be t squared, up to another scalar times 2 to the n. So I still have a polynomial of degree n or less. If I wanted to show commutativity, I have to show that p of t, the polynomial p plus the polynomial r is equal to the polynomial r plus polynomial of t. So I can write out p, I can write out r, and then I could break this down further, except I'm just going to say, by addition of polynomials, and I think that's still rigorous. Like, you can add this polynomial first to that polynomial, so you get r of t plus p of t, just because we know how to add polynomials from algebra. So there we go. For the additive identity, I'm just going to call that polynomial I for identity of t is equal to 0. Certainly I of t is in every p of n because I of t has degree 0, and so its degree is at most whatever n is. Like if n is equal to p3, certainly I of t has degree less than 3. So I of t is in every p sub n for all n. So looking at I of t plus some polynomial p of t, well, that's 0 plus your polynomial p of t, you add it, you get back p of t. Now we can talk about additive inverse for a given polynomial. That's just going to be our scalar -1 times our polynomial. And then we can show that p of t plus negative p of t. Here I have p of t, here I have negative p of t. When we add, we group our coefficients together So A minus A naught is 0. Having our A1 minus A1t, you can see it's equal to 0. Proving now the first property of scalar multiplication, this associativity with these two scalars, I named my scalars C and D. They're my real numbers. So C times D times P is equal to CD times P. So I start off with C times D times my polynomial. So here's my C and then D times my polynomial. So I multiply D right out times my polynomial, then I multiply C times my polynomial, and just by, you can always factor out a scalar out of your polynomial. So I have CD times my polynomial, which is this here. Distributive can be shown, these two distributive can be shown similarly algebraically. The multiplicative identity, you're probably not M4. Probably no surprise, the multiplicative identity, I'm just going to call it M of t, will be equal to 1. And I want to mention this to put this idea in your head. We're definitely going to elaborate and look at this idea in much more detail later in this course. But let's consider P3, polynomials of degree 2 or less. They can be represented by this vector, A0, A1, A2, and A3. So just taking the coefficients, you can have this, you can represent it by this vector, because what we're saying structurally is when we've defined vector addition and the scalar multiplication, they are structurally the same, R3 and P2. I simply cannot resist. Remember the waves example? They can also be represented by this vector. So what are the coefficients you're going to use? Do you remember in calculus when you did Fourier series? The coefficients in front of your sines and cosines, that will be what goes into this vector. Anyway, as I said, we are going to discuss that in much more detail later in this class. Our next example is the set of real-valued functions defined on a set D. D typically being a set of real numbers or some interval. Functions are added in the usual way. Likewise, scalar multiplication is the usual way. It can be shown that this is a vector space. So thinking about what that means, let's say we have a function f. It operates on some domain D. And here we have a function g, it operates on some domain D as well. And they map to some other set A or set B. Now we can add the two functions. We know how to add two functions. And they're still going to be operating out of the set D, and then they map to some other set, whatever it is, C. And the idea is that this is our function addition, is now we can think of f, these functions as vectors, these functions g as vectors, and then we can think of the function addition then as our vector addition. And you can see that it's closed, right? Because when you add f plus g, again, you're going to be operating out of D, or D is still your domain, so it's closed. Similarly, if you have some scalar a times f, and your domain is still D, but then when you finish, you're going to have a times whatever your normal values are. And I don't know what that set's going to look like, but let's just say it's going to equal to a prime. You can go through, function addition is commutative. It doesn't matter if you have f plus g, that's going to be equal to g plus f. And you can go through all of these, the identity, the additive identity is going to be the function that's 0. The additive inverse is the negative of f. So you can see that now we can consider functions as vectors. It's important to think of each function here, the f, the g, as a single object. It's a single vector. It's just one point or one vector in the vector space. Okay, now that we've looked at vector spaces, we can define a subspace of a vector space. And essentially, a subspace is just a subset H of V that is also a vector space. But when we want to show that H is also a vector space, we only have to prove three properties. One, that the zero vector of V is also an H. Two, that, and we have this note here, a subspace H of V is itself a vector space. So again, it's a subset of V that itself is a vector space. And the reason why we only have to prove these three properties is because these other properties, the other 7 properties of the vector space, are, I'm going to say in quotes, inherited, since H is also a subset of V. So the fact that it's commutative, well, since all the vector addition in V is commutative, that means since H is a subset of V under the same definition of addition and scalar multiplication, then the addition of vectors must also be commutative in H. Again, it inherits it as being a subset of V. But the things that H may or may not inherit is one, the zero vector. Also, it's possible if you have a subset that you could add to and escape the subset and still be in V, but not in H. So you have to show that H is closed under addition, and similarly you have to show H is closed under scalar multiplication. And our first example of subspaces is the set consisting of only the zero vector, and a vector space V is a subspace of V called the zero subspace, and written with these curly brackets with the vector z. And so first we need to show closure properties, and we also need to show that the additive identity is in there. To show our closure properties, we need to show it is closed under addition. Well, 0 plus 0 is still equal to 0. It's closed under scalar multiplication, so if you have a real number a, then a times 0 is still equal to 0. And the additive identity of the vector space, well, that's 0, the 0 vector, and by definition, it is in H, because H is here, the set of containing only the 0 vector. So by definition, the 0 vector is in H. So therefore, we can say that H is, or I'm sorry, this 0 subspace is in fact a vector space. Our next example is let P be the set of all polynomials with real coefficients with operations in P as defined for functions, because definitely polynomials are definitely a type of function. Then P is a subspace of the space of all real valued functions defined on R. And actually, we've already discussed how P is a vector space. The set of polynomials, we said that was a vector space. And we also said the set of functions is also a vector space. So also for each n greater than or equal to 0, Pn is a subspace of P, because Pn is a subset of P that contains the 0 polynomial. And the sum of two polynomials is also in Pn, and the scalar multiple of the polynomial is also in Pn. So let's break that down just a little bit. So I've broken up this little statement into two parts. First is that the set of polynomials with real coefficients is a subspace of real valued functions. And we know that because, well, one, to be a subspace, 1P has to be a subset of real valued functions. Well, that's true. The set of polynomials with real coefficients is a subset of real valued functions. And two, we've already shown that the set of polynomials is itself a vector space. But if we hadn't done that, we would just have to show that if you add two polynomials together, you still get a polynomial, but you can kind of intuitively know that's true. So it's closed under addition. If you multiply a polynomial by a scalar, you still get a polynomial, and also you know that. So it's closed under scalar multiplication. And last, P has an additive identity. That is, the 0 polynomial is equal to 0, because you add 0 to any polynomial, you get back the original polynomial. The second statement that I've broken out of here, which starts here, the also statement, is that Pn, polynomials of degree n or less, is also a subspace of P, and therefore a subspace of real valued functions. And we know that because one, Pn is a subset of P, I should say that. So it's a subset of P, right? The set of polynomials of degree n or less is certainly a subset of P. And we've also shown that Pn is itself a vector space. And you can go back and see the notes to show that it is closed under addition, vector addition. It's closed under scalar multiplication, and it does have the additive identity 0. The set of finitely supported signals S of f consists of the signal y sub k, where only finitely many of the y sub k are non-zero. Since the 0 signal, that's the 0 vector, with zeros infinitely to the left and zeros infinitely to the right, has no non-zero entries, it is clearly an element of S, because it has only finitely many non-zeros. So it has no non-zero entries, so it's an element of S. If two signals with finitely many non-zeros are added, the resulting signal will have finitely many non-zeros. Similarly, if a signal with finitely many non-zeros is scaled, the result will still have finitely many non-zeros. Thus, SF is a subspace of S. S was the doubly infinite space, the discrete time signals. Here we're getting back to Rn with more examples. So the vector space R2 is not a subspace of R3 because R2 is not even a subset of R3, right? R2 looks like this, x1, x2. R3 looks like x1, x2, x3. It is the case that H that looks like this, x1, x2, 0, is a subset of R3, right? It has this form, but maybe we don't use the second, it's only in the plane, but it's still in R3. And it looks like R2, although it is not in R2, because this is this point in 3 space, even though these are points in the xy plane. One more example, a plane in R3 not through the origin is not a subspace of R3 because the plane does not contain the 0 vector. That is, it doesn't contain 0, 0, 0. Similarly, a line in R2 not through the origin is not a subspace of R2. You have to go through the origin if you want to be a subspace because you have to contain the additive identity. Final topic is a subspace spanned by a set. So if you have a set of vectors, they're in the vector space V, then the span of these vectors is a subspace of V. We call this span of VP the space span or generated by these vectors. So given V1 and V2 in a vector space V, let H equal the span of V1 and V2. Show that H is a subspace of V. So we have this vector space, it has who knows how many vectors in it, but we can take 2 out. Consider the span, all linear combinations of those vectors, and that itself will be considered a subspace of V. Because we know V is a vector space, we know that a lot of the commutativity, associativity, that's going to work because it works, those things work for any vector in V. So the only 3 things we need to show are the 0 vector is in H, also H is closed under vector addition, and H is closed under scalar multiplication. So first the 0 vector is in H because 0 times V1 plus 0 times V2 is equal to 0. So they're in the span of V1 and V2. And also just a note, whenever you see span of V1, V2, you should think linear combination. So I've written my linear combination. I've shown when my coefficients are 0, I get the 0 vector. So it is definitely an H. Closed under addition. So if we have a vector u, which is a linear combination of v1, v2, and we have a vector w, which is a combination of v1, v2, when you add them together, you still get a linear combination of v1 and v2. So not too surprising. So that means that u plus v, if u is an h and v is an h, then their sum is also an h. So addition is closed. For scalar multiplication, I'm going to multiply some scalar a times my vector u, where u is a linear combination of v1, v2. So I have my scalar a times a1, v1 plus a2, v2. And because v1 and v2 are vectors in the vector space v, I can use this kind of distribution thing, and I can distribute the a. Multiply the a times a1, v1, a times a2, v2, then I can group my a1 and v1 together. A and a1 together. I can group my a and a2 together, and then I get that I have a linear combination now of v1 and v2. That means a scalar times some vector in h is still in h. So scalar multiplication is closed. We have another example. Let H be the set of all vectors of the form a minus 3b, b minus a, and b, where a and b are arbitrary scalars. That is, let H equal to a minus 3b, b minus a, b, where a and b are real. Show that H is a subspace of R4. I start by rewriting H so it looks more like R4. So I have a minus 3b, b minus a, and b. Now I can rewrite H so that I have kind of my a's grouped together and my b's grouped together. So I have a minus 3b. Here I just rearranged the a and b, so I have negative a and b. And then I have a plus 0b, and then I have 0a plus b. So now I can break this up into a scalar a times the vector 1, -1, a 0, and a scalar b times the vector -3, 1, 0, 1. And so h always has this form. H is always a linear combination of the vectors 1, -1, 1, 0, and -3, 1, 0, 1. And now I can make use of this formula here because the span of a set of vectors is just the linear combination of these vectors. And we have a linear combination here, which means that h is equal to the span of the vectors 1, -1, 1, 0, -3, 1, 0, 1. And by this theorem here, that means it is a subspace of V. And I should say in particular, it's a subspace of R4. Our next example, for what values of h, because we have an h over here, will y be in the subspace of R3 spanned by the vectors v1, v2, v3? So another way of writing this, I have y, and I want it to be in the subspace spanned by these three vectors. In other words, I want it to be a linear combination of my vectors v1, v2, and v3. So I have my -4, 3h is equal to x1, 1, -1, -2, x2, 5, -4, -7, and x3, -3, 1, 0. And that's equivalent to the matrix equation where I have A, which is just v1, the columns v1, v2, v3, times x equals my vector y. We know how to solve this. We do our row reductions until we get to this last equation here, which tells us -5 plus h must equal to 0. In other words, h must equal to 5. At this point, we've covered a lot, but we have covered all the material for this video. I do have, I think it's one more problem. No, actually, I have 3 more problems, and I'm going to suggest, since we've covered all the material, that after each problem statement, you pause the video to give the problems a try before you look at the solutions. The first problem is to show that h, the set of all points in R2 of the form 3s, 2 plus 5s, is not a vector. So it's not a vector space by showing it is not closed under scalar multiplication. So it tells you what property it fails to satisfy. And there's this hint: find a specific vector u and h and a scalar c such that cu is not in h. So what I did is I started with this kind of hint here. I let s equal to 2, just so I could find a vector u and h. So when s is equal to 2, on the top I'm going to get 6, and over here on the bottom I'm going to get 12. Then I just randomly picked a scalar, s equals 3, and I kind of made it, well, anyway, I picked a scalar, s equals 3. So then 3u, I'm going to multiply by 3, that's 18, and that's on the bottom will be 36. So this, I want to know if it's still in this form. If it's closed, it'll still be in the form 3s plus 5, 3s, and then 2 plus 5s. If the top is in the form 3s, that would be equal to 3 times 6, because the top is 18, right? But that would mean s is equal to 6. So I plug in my 6 here, and if I add 2, I'm not going to get 36, I'm only going to get 32, which means that when I choose s equals 2 and I have the vector 6, 12, which is in h, when I multiply by the scalar, I am no longer in h. I no longer have that form. So this is my example that disproves that h is a vector space. So let w equal the span of p vectors, where these p vectors are in a vector space V. Show then some vector vk between 1 and p. So one of these vectors is in W. And the hint is first write an equation that shows v1 is in W, then adjust your notation for the general case. And I have to tell you, I went straight for the general case, but you can do it this way if you'd like. So first I wrote W. Since it's equal to the span of these p vectors, I wrote this as a linear combination of the p vectors. So I have v1, v2, up to, and I included vk as somewhere in here, and then I have vp, right? So now I'm going to say let all x of I equal 0 except for x of k. which is my coefficient in front of v of k, I'm going to let that equal to 1. So what I have done is I've written a linear combination of the p vectors that's equal to v sub k. And my linear combination is where all the x sub I is equal to 0, except for this one, x sub k is equal to 1. So that's allowed. It's a linear combination. So what I have is v sub k is in the span. It's a linear combination of these vectors, so it's in the span of these p vectors, which implies that v sub k is in W. This last problem, an n by n matrix A is said to be symmetric if A transpose is equal to A. Remember, A transpose is where the columns become the rows, or you could say it vice versa. Each row becomes the new column. So row 1 becomes column 1, row 2 becomes column 2, etc. Let S be the set of all 3 by 3 symmetric matrices. Again, symmetric means A transpose equals A. Show that S is a subspace of M 3 by 3. And the M 3 by 3 is a vector space where M is 3 by 3 matrices. And the first thing I want to note is that the set of all n by n matrices is a vector space. And we'll consider 3 by 3 matrices and kind of hand wave our way through this just because I think this is worth mentioning. You should know that the set of matrices is a vector space. So one, if you add a 3 by 3 matrix to another 3 by 3 matrix, you're going to still get a 3 by 3 matrix. So it's closed under addition. If you multiply a 3 by 3 matrix by a scalar, you're still going to have a 3 by 3 matrix. So it's closed under scalar multiplication. You know, addition of matrices is commutative. Remember, multiplication is not, but addition is commutative. Associative, it's not too hard to see. It's also going to work out. The additive identity, that's the matrix with all entries 0, right? So if you add 0, 0, 0, 0 to any 2 by 2 matrix, you're going to get back your original 2 by 2 matrix. And then additive identity, if your matrix is A, B, C, D, then the additive identity is going to be minus A, minus B, minus C, minus D. Or you can think of that as the minus 1 scalar times your original matrix A, B, C, D. So this is all going well. You can also, you know, your scalars multiplied your matrix, you're still going to get, these are all going to work. You can kind of think about that. The multiplicative identity, again, is your identity matrix, your 1, 0, 0, 1. And you can, we've been working with that, so I'm not going to verify it for you. But this is kind of my hand wavy thing, that all the set of all n by n matrices, and I just talked about 3 by 3, but the set of all n by n matrices is indeed a vector space. So now let's go back and let's prove that the set of symmetric matrices, where A transpose equals A, is also a subspace. And also, I feel like I'm always giving you extra notes. I wanted to see what the symmetric matrices look like, so I wrote a 3 by 3 matrix for A, and you know, this is the first row, first column entry. This is the first row, second column entry. That's what these indices mean. The I is the row, the J is the column, right? Now I'm going to look at this matrix and take the transpose. So I'm going to take this first row and make it into the first column. The second row becomes the second column. The third row becomes the third column. So what makes A transpose equal A? Well, first of all, we see that the diagonal, that's nice, it kind of stays. Then what we need are the things across the diagonal to be equal, right? We need this, because here I need A21 to equal to A12, right? If I want these two matrices to be equal. I want A12 to be equal to A21. And I want A13 to be equal to A31, and A23 equal to A32. So things across the diagonal need to be equal. So this is the general form of a symmetric matrix. The second thing I'm going to say, and this is what will really start the problem, is since we already know that the set of 3 by 3 matrices, that was my alarm, sorry. The set of 3 by 3 matrices is a vector space. The set of symmetric 3 by 3 matrices is a subset of all the 3 by 3 matrices. So now we can use the fact to be a subspace. We only need to verify these 3 conditions. One, that the 0 vector is in H, that H is closed under vector addition, and H is closed under scalar multiplication. The first one's easy. The 0 matrix, it's symmetric. Look at it. Okay. Addition is closed. So let A and B both be symmetric. So in other words, A transpose equals A and B transpose equals B. So we're going to consider A plus B transpose, and what we want to show is that it's equal to A plus B. But from our properties of transpose matrices, and I'll let you look back at that, this is equal to A transpose plus B transpose. Since A is symmetric, that's equal to A. Since B is symmetric, B transpose is equal to B, and I have proven what I wanted to show. Scalar multiplication, again, it depends on you knowing the properties of transpose matrices, so I'll let you take a look. But let A equal A transpose. What we want to show is C times A transpose then is going to equal to C times A. That's what we want to show. So C times A transpose is equal to, well, now we know A transpose is equal to A because A is symmetric, so C times A, which is exactly what we wanted to show. So reviewing really quickly what we've gone over through this video, and it was a very long video. I hope you got something out of it. One, we talked about vector spaces, and what a vector space is it's a set of vectors along with two operations, vector addition and vector scalar multiplication. And the thing about this set and the two operations is they satisfy these 10 properties, some closure properties, properties of addition, and properties of scalar multiplication. Then we said a subspace, and I'm going to use this definition here. If we have a subspace H of V, then H is a subset of V, and H is also a vector space itself. But because V is already a vector space, these kind of commutative, associative properties, additive inverse, associative distributive properties, they are already satisfied. So if we wanted to prove that H is a subspace, we only need to prove these three, the closure properties and that the identity, the additive identity is in H. So these three conditions. And then last we talked about a subspace spanned by a set. So if you had a set of vectors and you considered the span of those vectors, that is a subspace of your vector space V. So that's it for this video. Thank you for watching.